Hello everyone, this is Hassan Termos again. I hope you're all safe, I hope you're all doing well, I hope you did well in your EECE330 Quiz 1. This is the second revision session for EECE330 offered by the Cultural Club of the South. So, we've received a lot of positive feedback regarding the first revision session, so we're gonna do it again. This session is aimed to help you prepare for the second quiz in EECE330. We're gonna solve a few problems on linked lists, binary search trees, red-black trees, inheritance, and I hope you find those problems beneficial. And as before, we're gonna try to go through the thought process rather than just give you the solution. So let's jump in. This first problem is from LeetCode. Other problems are gonna be from previous EECE330 exams. So reverse nodes in K group. We're given the head of a linked list and we're asked to reverse the nodes in the list K at a time and return the modified list. K is a positive integer and is less than or equal to the length of the linked list. If the number of nodes is not a multiple of K, then left out nodes in the end should remain as it is. You may not alter the values in the list's nodes, only nodes themselves may be changed. So we're also gonna try to avoid creating new nodes, we're just gonna try to modify the connections. So anyways, what's the problem asking us to do? Consider this linked list. Imagine we divide it into chunks of size k, here k is equal to 2. So we divide it into chunks of size k, except for the last chunk, which may be of size less than k if we don't have enough nodes. So we're gonna have to reverse every chunk. So this chunk is 1, 2, it's gonna become 2, 1, 3, 4 is gonna become 4, 3, and this last chunk is gonna remain as is. So this is a second example where k is equal to 3. So this chunk is the values in the nodes in this chunk were 1, 2, 3. They're going to become 3, 2, 1. This last chunk, which isn't of size 3, is going to remain as is. So 4, 5 is the nodes with values 4 and 5 are going to stay in that order. And note that there is this follow-up question. So can you solve the problem in O of 1 extra memory space? Okay, so we're going to try to do this. We're going to try to solve it in O of 1 extra memory space. I encourage you to pause, try to ponder the question, try to think of a solution, maybe think of a partial solution, maybe even try to implement and submit on LeetCode. Now I'm going to present the one thought process that you may go through. So consider this linked list and consider that k is equal to 5. So this is the first chunk we're gonna have to reverse. This is the second chunk. And this last chunk of size 1, we're just not gonna touch it. We're not gonna reverse it. So one way to approach this problem is, let's try to reverse every chunk. So say we reverse this chunk first, then we get this. The second chunk, we're not gonna touch it yet. We haven't reached it, so it's gonna stay as is. And of course, this final small chunk is gonna stay as is. And then we try to reverse the second chunk and so on. So this chunk is reversed, this chunk is still reversed, and this chunk is not touched. So this is one way to approach the problem. And there are a few observations that we can make. So first of all, note that the head of the list is changing. So the head was this node having the value 1. But by the end of our process, the head became this node, having the value 5. So we have to keep track of the node. Also, note that during this process of reversing this chunk, not only did we change these pointers, but we also had to change this pointer. So this pointer that is going out of the last node in the previous chunk is gonna have to change. 1 used to point to 6, but now it's gonna point to 10. So to clean this up a little, we're gonna have to keep track of the last node in the previous chunk, which is 1 in this case, and we also have to change that pointer. Hopefully that makes sense. And we still have to figure out an algorithm that would allow us to reverse a certain chunk in the linked list. So for now, we're kind of black boxing it. We're assuming that we have this algorithm ready, but we're gonna have to figure it out eventually. So for now, let's just do that. Let's assume that we have this function that, given a pointer to the first node in a chunk and the last node in a chunk, given this pointer, it's able to reverse this chunk. And assuming this function is there, it's available to us, let's try to implement the kind of high-level logic of our entire algorithm. So let's try to implement this. Oh, also note the structure of the list node. So we have this struct called list node. It holds a value. It holds a list node pointer to the next node. So this is very similar to the LL node class you might have seen in class. And it has this constructor that takes no arguments, and it sets val to 0 and next to null. And it has this constructor that takes a single value, and this constructor that takes a single value and a pointer to a list node. Okay. So let's create a new file. Let's call it P1. Let's copy over the definition of this struct so we can keep it in front of us just in case we want to. Well, let's keep this as a comment. So yeah, just in case we want to run the code or we want to take a look at the struct at any point, it's a good idea to have it in front of us. And in lead code, in this problem, we're gonna have to implement our function here. So it's inside a class called solution. We have this public method called reverse k group, and this is where we're gonna implement our solution. And this is just a lead code thing. It's not really part of the actual problem. So okay, so the logic we had was go over every chunk and just reverse it. And we said we have to keep track of those details, that the head is gonna change, the pointer of the last node in the previous chunk is gonna change. So we're gonna have to take care of these details. But first, the trivial case, where k is equal to 1, we just return head. So if k is equal to 1, we're gonna divide the list into chunks of size 1, and then we're gonna reverse every chunk, but since it's of size 1, it's not really gonna change. And then we're gonna return the list. So basically nothing's gonna change in the list. So for k equal to 1, we just return head. So for larger values of k, let's go back to the drawing board and try to be more concrete about what we want our algorithm to do. So let's try to figure out what pointers we need to keep track of, what values we need to keep track of, etc. So first of all, we're considering this chunk. So let's say this pointer, let's call it P for now. This pointer is pointing to the start of the chunk. This pointer Q is gonna point to the start of the chunk initially as well. But then we're gonna have it jump K steps forward. So it points to the last node in the chunk. Okay? And remember, we're assuming that we have this function that we can give those two nodes to. So we give it the first node in a chunk and the last node in a chunk, and it reverses this chunk. Okay? So what specifically do we expect this function to do? What we want it to do is, first of all, we don't want 5 to point to 6 anymore. We want it to point to 4. And note that I'm not going in the order that the function is going to execute those steps. It might not change the pointer of this node in the start, but I'm just going over what we want its effect to be. So in effect, we want 5 to point to 4 instead of 6. We want 4 to point to 3. And you can see this here. So 5 points to 4, 4 points to 3, 3 points to 2. We want 2 to point to 1. And then we want 1 to point to 6, right? And note that this function kind of has access to the node 6, because initially 5 used to point to 6. So this function can maybe save 6 in a variable, and then it can have 1 point to this node 6. Okay. So in effect, what we did here is basically this. You can follow those arrows, follow the pointers, and you'll reach the conclusion that we did achieve this. And note that now Q, or this end pointer, this pointer that's pointing to the end of a chunk, is now pointing here. And P is now going to be pointing here, because P is pointing at the node holding the value 1, which is now here. So now we're going to go over to the next chunk. So we're going to move P here. We're going to put Q here, and then we're going to advance Q 5 steps forward, because in this example case 5. And then we're going to go over the same process again. Instead of 10 pointing to 11, we want it to point to 9. 9 is going to point to 8. 8 is going to point to 7. 7 is going to point to 6. And 6 is going to point to 11. So everything seems okay, but note that 1 is still pointing to 6. This is a problem here. And this function, we're giving it 6, we're giving it this node and this node. So it doesn't really have access to 1, because this is a singly linked list, so we can't go backwards easily. So taking care of this one is going to be outside this function. So we want this function to just reverse this chunk, make sure that those nodes in this chunk have their pointers set right. This is its sole responsibility, and it's good design to have a function have a single responsibility. So the single responsibility of this function is those 5 nodes, I want them to point to the correct position, or at least temporarily, because for example here 1, its pointer is going to change, but it was pointing to the correct temporary position that we want it to point to. So take care of those 5 nodes, but this extra node, which is actually the last node in the previous chunk, we're going to have to take care of this. This function is not gonna take care of it. So hopefully you got the logic. We pass the starting node and the ending node. We give it to this function. This function takes care of the nodes in between. And we're going to have to be careful about this. And we're going to have to be careful about head. Remember those 2 observations? You have to be careful about the last chunk, the last node in the previous chunk, and about updating the value of head. So anyways, let's try to implement the logic we've gotten so far. So to keep track of the first node in a chunk and the last node in a chunk, which we call P and Q, let's give them more descriptive names. Let's call it current chunk start, and initially it's equal to head. So the first chunk starts at head, and we're gonna have a loop. So we'll take care of the condition later, but we're gonna have some sort of loop that keeps going as long as we have chunks to take care of. So as long as there's a chunk that we should reverse, or any chunk for that matter, this loop is also gonna take care of this last chunk that may be of size less than k. So as long as we have no nodes to take care of, just keep this loop running. So in this loop, we're gonna have this current chunk end pointer, and initially, as we already established, it's gonna point to current. It's gonna be equal to current chunk start, so it's pointing to the same node that current chunk start is pointing to. And we wanna advance it k nodes forward. So let's say we have a simple for loop. where int I equal to 0, I less than k, I plus plus, and we're just gonna advance cur chunk end. So cur chunk end is equal to cur chunk end arrow next. And you may already have this internal alarm going off that we're dereferencing current chunk end without checking if it's null. So we're gonna have to add this condition. So check if that current chunk end is not equal to null pointer. So this seems to be going fine so far. So after this, we're gonna have our current chunk start pointer, we're gonna have our current chunk end pointer, and let's pass them into this black boxed function, this function that reverses a specific chunk, and assume that it will take care of that. So reverse chunk, actually let's call it reverse group, because this is called reverse k group, so just sticking to the similar names. So yeah, reverse group, we pass in current chunk start and current chunk end, and recall this function we're gonna have to implement is gonna be reverse group, and it takes a list node pointer start and a list node pointer end, and it reverses the chunk. And we're gonna come back to this obviously. So anyways, after this is reversed, we're gonna have to take care of updating our variables for the next iteration. So we're gonna say cur chunk, okay, so cur chunk start is gonna have to be updated. Now we don't really have to worry about cur chunk end because its value is being set here. So what do we have to set cur chunk start to? So if you think about it, we want cur chunk start to point to the start of the next chunk, which may tempt you to do something like this. So cur chunk start is cur chunk end next. So, oh, I forgot a semicolon here. So wherever cur chunk end was pointing to, now cur chunk start should point to the next node after that. But recall from the visualization we went through that after our process is over, cur chunk end is gonna point. Okay, so this is after this is the first intermediate step we're gonna get to. So cur chunk end is gonna point here, and cur chunk start is gonna point here, because because of the by nature of reversing the chunk, the start is gonna actually point to the end. So what we wanna do is cur chunk start is equal to cur chunk start arrow next. So hopefully this makes sense, because after reversing the list, cur chunk start is actually gonna point to the last node in that chunk. So moving on, this let's go back now to this condition for the while loop. We want to keep going as long as there are new chunks to take care of. So we could just check if current chunk start is not equal to null. So if current chunk start is null, this signals that there aren't any more chunks to take care of. Okay, so this is a good start. Now let's start building up from here. So remember our two observations. First of all, we have to update the head, and second of all, we have to update the pointer of the last node in the previous chunk. So let's take care of the second observation first. So let's keep track of a list node pointer, call it previous chunk end, and initially it's equal to null pointer, let's say, because the first chunk there is no previous chunk when we're dealing with the first chunk, so let's just set it to null pointer initially. So now we're gonna have to first of all, we're gonna have to update the pointer previous chunk end next. So we have to update this. And we also have to update, like by the end of the loop, you have to update previous chunk end itself. Because when the loop goes into when we go into the next iteration, we want it to point to the last node in the previous chunk with respect to this new chunk we're dealing with. So previous chunk and next is gonna have, so we want this the last node in the previous chunk, we want it to point to, so here for example, we want 1 to point to 10 after we reverse this second chunk. So we want 1 to point to the end of our new chunk. So previous chunk next is gonna be equal to current chunk end. Hopefully this makes sense. Okay. Otherwise, so, and we're gonna have to check if previous chunk end is not equal to null pointer, because we don't want to dereference null. So otherwise, or actually after that, we're gonna want to update previous chunk end. So after everything is done, let's just make sure that previous chunk end is updated. And remember, we want it to point to the last node in the previous chunk, which now is actually current chunk start rather than current chunk end, for the same reasoning that we used here. Oh, and I forgot a semicolon here. Okay. So that takes care of our second observation, which is that we have to update the last node in the previous chunk. And as for the first observation, we can actually take care of it here. So if previous chunk end is null, then we're dealing with the first chunk. And when dealing with the first chunk, we know that the current chunk end is gonna be our new head. Because for example here, when we reverse this chunk, now this last node is our new head, right? Okay. So I believe this all makes sense. And we're still gonna have to go back to this function. But let's just go over this again and make sure we didn't forget any core logic, any core part of our algorithm. So first of all, we take care of the trivial case. Then we keep track of the start of our current chunk and the end of our previous chunk. Then as long as our start is not null, so there are still chunks to take care of, we're gonna forward the current chunk end pointer k positions forward, and then we're gonna make sure the last node in the previous chunk points to the correct node, and then we're gonna reverse the current chunk and update our variables, preparing for the next iteration. Now, one thing that we have to take care of is if we're at the last chunk. So for example here, notice that we might break out of this loop, or this loop may terminate because of this condition. So if current chunk end reaches a point where it's null, then that means we don't have enough nodes to take care of a new chunk, so we just have to break. So if current chunk end is equal to null pointer after this loop, then we just have to break. So this should take care of this entire function. Now we just have to look closely at the logic behind reverse group. Let's zoom in to a single chunk and consider how this function is going to deal with it. So let's look at this chunk, which is 6, 7, 8, 9. And remember here k is 5, so this chunk is of size 5. So this function receives a pointer to this node and a pointer to this node. Let's call them P and Q. And it doesn't really receive anything else as an argument, but it does have access to this node here, and actually every node after that if there were, by just traversing the linked list. But it doesn't have access to any nodes here. So here we would have one in this intermediate step here. So here there's one, but we don't have access to that, as we've already discussed before, because we can't go backwards in the singly linked list. So let's think about how one might build up a solution to implementing this function. So the first idea one might think of is, let's just traverse the linked list and make every node point to the node before it. So starting at 6, we're gonna quickly realize that 6 is kind of a special case, because every node is gonna point to the one before it, except for 6, which is gonna point to 11. So let's just say we take care of 6 at the end or before all the nodes. Just take care of it as a special case. And let's think about how we can take care of the other nodes. So let's say we start at 7, which is P arrow next. So if we try to start at 7, we want 7 to point to 6, right? Okay. So how do we get access to 6? How can we make 7 point to 6? The idea here is, because this is a singly linked list, you can't go backwards through 7. So the way we're gonna do this is just keep track of another pointer which points to the node right before the one where we reach. So for example, if we reach 9, we want a pointer pointing to 8, so that we have access to 8, so we can make 9 point to 8. So anyways, so that takes care of that. Let's say we're moving those two pointers together like this. Okay, so let's say we remove this tie, let's say, and we make 7 point to 6. So that so looking at this from a C++ perspective, this is just changing the value stored in this pointer and making this pointer point to another node. So these steps are happening simultaneously. The moment you want to make the pointer of this node point to 6, you're gonna directly have to remove this link between 7 and 8. But when we remove this link, we can no longer reach 8 through 7. So this traversing we were gonna do, so this pointer, it's not gonna be able to go through 7 to 8, because now 7 no longer points to 8. So how do we take care of this? One way to take care of this is just have a third pointer point to the node right after the one you're taking care of. So let's say this is the node we're taking care of. We have those two, let's say, sub pointers, one pointing right before it and one pointing right after it. The one pointing right before it is so we have access to the node that we want our current node to point to. So we want access to 6, so we can make the node having the value of 7 point to it. And this other pointer is so that we can advance later on. So after we make 7 point to 6, we want to advance to the next node. So we're gonna use this pointer to facilitate the advancement. So this is the idea. Let's go over it. Let's go over the steps. So initially, this is what we have. We have this pointer here. We have a pointer right before it, a pointer right after it. What we're gonna do is we want to make 7 point to 6. So the way we're gonna do this is just simply we're gonna make actually let's give them names. So let's call this let's call them ABC. So we're gonna say B arrow next is equal to A, right? So this is gonna be like this. And then after we do this, we're actually done fixing the pointers. Now we just want to advance. So the way we're gonna advance is just say A is equal to B. So now A is here. And then, oh, actually, let me move so A is here. And then we're gonna say B is equal to C. And then let's just say C is equal to B arrow next, or C is equal to C arrow next. It won't matter a lot here. And now we do this again. So A is pointing to 7 now, B is pointing to 8, C is pointing to 9. Let's do this again. Make B arrow next point to A. This is this step here. Oh, let me actually do A is equal to B, B is equal to C, as I said, and then C is equal to B arrow next. Okay. So yeah, 8 is gonna point to 7, and then the next step is A equal to B, then B equal to C, and then C equal to B arrow next. And again, we just say B arrow next is equal to A, and then we say, and then we do A equal to B, B equal to C, C equal to B arrow next. And then I'm gonna remove Q just for cleanliness. But yeah, so then we do this again. We're gonna make 10 point to 9 here. And then A is equal to B, B is equal to C, and C is equal to B arrow next. And we know that we want to stop whenever B is outside the chunk. So whenever B, if we bring Q back, we know we want to stop whenever B is equal to Q arrow next. Right? Okay. So if we do this, yeah, I hope this is clear. This basically covers it. Oh, and there's still this step of making 6 point to 11. And now note that we no longer have access to 11. So we're gonna have also to store this on the side, like in a separate pointer. And you might think we're using a lot of pointers, but it's still O of 1 space. So we're adhering to the constraints that we want to adhere to. And this is a simple solution of whatever you need to keep track of, just keep track of it. So hopefully this makes sense. And now we're gonna try to implement it. So to implement this, first of all, let's keep track of this point, this node here. So this node is the one right after Q. So let's say we have a list node pointer. Let's say this is the node that's gonna be the start of our next chunk. So let's call it next chunk start, and it's equal to end arrow next. So we just want to keep track of this. And now let's set up A, B, and C, but let's give them more descriptive names. So let's call them current node and current node previous and current node next. So current node previous is gonna start off being start, because remember we're gonna just skip taking care of P, or taking care of the first node in the chunk, and we're gonna take care of it at the end. For now we're gonna worry about the second node onwards. Okay, so current node prev is equal, oh, we're gonna have to add these for each of them. And this is just how C++ works. You just have to add this to explicitly state that each of those or each of these variables is a pointer. So current node prev is equal to start, and current node is equal to, let's say, current node prev next. And you could have said we could have said start arrow next, but it's nice to say to establish this relationship right off the bat, that current node is the node right after current node prev. So then we have current node next is equal to current node arrow next. Okay. Now let's say while, okay, so we want some sort of loop. that's gonna keep going until B reaches the start of the next chunk. So while current node is not equal to next chunk start, so again, while this B pointer, our middle pointer, this one here, while it hasn't reached 11, we want to keep doing this process, right? So while current node is not equal to next chunk start, we're gonna keep going. First of all, let's take care of the making the node point to the one before it. So current node next is equal to current node previous. So now we've taken care of this step of the process. So if we go back to our original list, and A, B, and C are pointing here. Okay, so now we've taken care of this part of the process. So now 7, the pointer in the node 7 is pointing to the node before it. And then now we want to start updating A, B, and C. So this is literally it for updating for actually fixing the pointer of the node. Now we're gonna start advancing A, B, and C. So as we said, we want A equal to B, which means we want current node previous equal to current node. And then we want B equal to C. So current node is equal to current node next. And then C is equal to B arrow next. So current node next is equal to current node arrow next. And this is basically it. There's just one small thing that we have to take care of, and that's that here we're dereferencing current node. So we've already checked that current, here we're implicitly checking that current node is not equal to null. Why? Because the fact that we are calling this function means that end is not null, right? Because looking at reverse K groups, if end was null, then we would break. We wouldn't be calling this function. So the fact that we're calling this function means end is not null. So here it's safe to dereference end, but we don't know if end arrow next is null or not. But it doesn't really matter, because here we're checking that current node is not equal to that. So we're checking that current node hasn't reached that node yet. So even if it's null, we're guaranteed that current node is not null. That's the important bit. We know current node is not null. But here, when we assign current node equal to current node next, we're not really sure that current node next is not null. Because looking at this visualization, let's say the linked list ended at 10. What we're gonna do is, we're gonna update the pointer for 9, then we're gonna update the pointer for 10, and then we're gonna jump forward. But once we jump forward, we're not guaranteed. So let's take a closer look at how we're jumping forward. So we're forwarding A to B, and then B to C. And remember, here we are basically at null. And now we're saying C is equal to B arrow next, but B is null. So we have no guarantee that at this point here, we have no guarantee that current node is not null. So we're gonna have to actually check that. So if current node is not equal to null pointer, then we want to do this. Otherwise, so if it's null, what do we want to do? If it's null, then we've reached the end of the list. So there's nothing left to reverse. We might as well just break. We're done with this function. And in fact, we're done with the entire function. So let's go over this logic really quickly once more. So first of all, we keep track of the first node in the next chunk, which may be null if there's no next chunk. And we're keeping track of this specifically for this if condition. So we're keeping track of it for this if condition, and also we should be using it somewhere else. I think I forgot this. Yeah, we should be updating start so that it can point to next chunk start. Yeah, so we're using it here and we're using it here. Here we could have used end arrow next, but we can't use end arrow next here because the node pointed to by end is gonna be changing as part of our loop. So we don't wanna assume that the 10 is gonna keep pointing to 11. So when 11 was here, we don't want to assume this is gonna stay because it's not. 10 is gonna point to 9 at some point, and that would mean our condition is vulnerable. So we're just gonna save the first node in the next chunk here, and we're gonna use it in this condition. So anyways, then we're gonna make a node point to the previous to the node right after it, and we're gonna update our pointers, making sure to not dereference null. So hopefully this is all clear. I think let's try to test this. So int main, just so we don't forget to return 0. Let's say we have this list node n1. Let's give it a value of 5. Actually, let's call it n5 to avoid any confusion. And let's say we have n4, 3, 2, and 1. Okay. Oh, and n4 should point. So we're gonna pass in the address of n5, so it points to it. n3 is gonna point to n4, so the address of n4. Here we're gonna pass in the address of n3. And this is just testing the code. It's not really part of the solution. Okay. So now let's say we solution s, then let's call the function through it. Let's pass in the address of n1, and then k is equal to 2, and we're gonna want to store the return value in x. But we should be actually returning head here. Yeah, so after everything is said and done, we're gonna have to return the head of the new list. Okay. After that, let's iterate for int I equal to 0, I less than 5, I plus plus. Let's see out the val. Then let's advance x. Okay. For cout, let's include audio stream, and let's do using namespace std. Okay. Let's try to run this. Okay, so the output we expect is 21435, but that's not what we're getting. So there seems to be some error in our code. Let's try to trace our code and find the problem. Okay, so we are starting with this list. 1, 2, 3, 4, 5. Okay, so first of all, we're checking if k is equal to 1, which is not true. Then we have cur chunk start. I'm gonna call it s here for start. So let's say this is s. It's at head, and then prev chunk end is null. So let's say previous end is null. Okay, and we go into the loop while cur chunk start is not equal to null pointer, which is true. The loop is gonna start. Cur chunk end is equal to cur chunk start. So let's say, oh, actually, let me put start here and here. Okay, and then for int I equal to 0, I less than k, and char chunk end not equal to null pointer, I plus plus. So basically we're gonna advance it k times, so 1, 2. Okay, so this seems to be an issue. I think I overlooked this. The thing here is the chunk is already of size 1, so we want to advance it only one time in this case, which means we want to advance it k minus 1 times in general. Because we're not starting from a chunk of size 0 and then going up to k. We're starting already from chunk of size 1. So yeah, this is one issue. Let's go on to see if we're gonna find any others. So then char chunk, if char chunk is equal to null pointer break, this is false, so we're gonna keep going. So if previous chunk end is not equal to null pointer, this is true, then previous chunk end next is current chunk end. So now previous end is gonna be here after we've made this correction. And then we go on, we reverse this chunk. So assuming the logic here is correct, let's assume it's correct for now, and then if something else turns out to be wrong, then we'll try to revisit the logic there. But assuming this is correct, current chunk start is equal to current chunk start arrow next, so we're moving start here. And then previous chunk end is equal to current chunk start, so previous chunk end is equal, so we're moving previous chunk end here. And this is after this is all reversed, so this is gonna be 2, 1, and end is gonna be here. Okay, so what we should do is, I think we should switch those. So we want to move previous chunk end to current chunk start before we actually move current chunk start forward. But yeah, assuming this is correct, I believe this should be fine now. Let's try this. Okay, so this gives the expected output. Let's try to submit it on lead code, where many more tests are gonna be run on this. So let's try to submit. Okay, so it seems to be correct. It was accepted. So yeah, hopefully you've understood the thought process here. Hopefully you benefited from this problem. It's a pretty long one, and it's kind of complicated. The implementation is kind of annoying, but hopefully you found it useful. Yeah. On to the second problem. We're going to be solving problem 3 from the fall 2019 quiz 2. Augmented binary search trees. Consider the following variation of binary search tree nodes, where a node has an additional member variable called size. So this is the regular BST node, but with this extra member variable. The purpose of the variable size is to indicate the size of the subtree rooted at this node. An example of an augmented binary search tree with integer data can be seen below. So here we can see that this is a regular BST, where the nodes to the left of a certain node have values less than it, and the nodes to its right have values greater than it. But there's this extra piece of information, or this extra member variable in every node, which is the size of the subtree rooted at it. So for example here, size equal to 4 indicates that the size of this subtree here is equal to 4, so it consists of 4 nodes. Here size equal to 2 indicates that this subtree here consists of 2 nodes, and so on. So in part A, we are asked, what is the relationship between the size of a node and the sizes of its children? Okay, so if we have a certain node M, and it has 2 children, n dot left and n dot right, and those 2 children may be roots to bigger, to some big subtrees, right? So there may be multiple descendants here. So the observation is, if I know the number of nodes in n dot left, in this entire subtree rooted at n dot left, and I know the number of nodes in this entire subtree rooted at n dot right, how can I quickly calculate or directly calculate the number of nodes in this entire subtree? It's simply the number of nodes here, let's call it x, plus the number of nodes here, let's call it y, plus 1 to account for the node itself. So if it has two children, we're going to take the size of the left child, the size from the right child, add them and add 1. If one of the children are missing, we're just gonna treat it as having a subtree of size 0. So hopefully this makes intuitive sense to you. Let's write this down. So for every node n, you can say n dot size is equal to x plus y plus 1, where x is equal to n dot left dot size if n dot left is not null. So if n does have a left child, oh sorry, if n dot left is not null, yeah. So if n does have a left child and 0 otherwise, and then y is going to be defined similarly but for the right child. So n dot right dot size if n dot right isn't null and 0 otherwise. We could also define the size of null to be 0. So we could say that n dot size is equal to the size of the, let's say the size of n dot left plus the size of n dot right plus 1, where we define the size of null to be 0. So this is a different approach. Okay. Now on to part B. Describe in pseudocode an algorithm verify sizes of root that returns true if all the sizes in the tree are correct and returns false otherwise. For example, it should return true given the tree illustrated above, but false given the tree illustrated below. What is the running time of your algorithm? Justify your answer. So in this tree, the sizes here are correct, but the size of in this node is incorrect. So size is set to 5, but in reality this subtree consists of only 2 nodes. So we're gonna have to catch this error. Okay, so how can we do this efficiently? So first of all, observe that if I have this node n and it has some left child, some right child, then okay, assume that we know for a fact that in the subtree rooted at n dot left, assume we know that the sizes are correct here, and that we know the sizes are correct in the subtree rooted at n dot right. How can we check if the size stored in this node is correct? So again, assume we know that the sizes here are correct. We know the sizes here are correct in all the nodes that are descendants of n dot right. How can we make sure that the size stored in n is correct? We can simply check for the relationship we just established here. So if this relationship holds, then we know the size of n is correct. Otherwise, we know that the size is incorrect. So this is exactly what we're going to do. So we're going to proceed recursively. We're going to check, we're going to verify the sizes of the left child and the right child. And then, assuming the sizes are correct, we are going to check the size of the parent in O of 1. Otherwise, if one of those is incorrect, or if we are not able to enforce this relationship with the parent, then we're just going to return false because we're guaranteed that there is at least one node with an incorrect size. So let's try to define this. It's called verify sizes. So we're going to define verify sizes of root. So first of all, we're going to check if root is null. Then we're going to return true, because if it's null, we just want to ignore it. We don't really, we don't want it to affect our answer. So if root is null, we just return true. Now we check if root dot left is not equal to null. Then set x equal to root dot left dot size. Otherwise set x equal to 0. So this is just establishing these definitions for x and y. And again, you can simplify this by defining the size of null to be 0. And then we have if root dot right is not equal to null, then y is equal to root dot right dot size. Otherwise it's equal to 0. So now we have the values for x and y. Now what we're gonna do is check if verify sizes return false for root dot right, for let's say left first. If it returns false, then we know that there is at least one node with an incorrect size. So we return false. And then we check the same thing for the right child. Root dot right. So we return false here. And if we pass those two checks, then we still have to check the relationship we established earlier. So if root dot size is not equal to x plus y plus 1, then we return false. Otherwise, if all those checks are passed, only then do we return true. So let me try to have this appear all together. Yeah, so this is the algorithm. Okay, this is functional again. Yeah, so verify sizes of root. First of all, we check if the root is equal to null. We just return true. And here we just establish the value of x. We can simplify this again by defining the size of null to be 0. And here, this is the same thing for y. And then we are checking if not all the sizes in the left subtree are correct. If one of them is not correct, then we return false. The same thing for right, we return false. And then we try to enforce this relationship we established earlier. And if it's false, then we return false. If we're able to enforce it, then we return true. So hopefully this is all clear. Yeah, I think this should be fine now. Now on to part C. So suppose we have an augmented red-black tree, i.e. as above, each node has a size member variable. So it's basically the same as explained above, but with the properties of a red-black tree. So one significant property or one important property is that it's balanced. So describe in pseudocode an algorithm select of root k, which given an augmented red-black tree and an integer k, returns the kth smallest element in the tree in O of log n time. So for example, given the tree in figure 1, for k equal to 3, select returns 8. So here, the third smallest node is 8. And for k equal to 5, it returns 10. So the fifth smallest node is 10. And for k equal to 1, it returns 3. And so on. So how can we approach this? I'm gonna show you two approaches to this. I was able to come up with the first solution. Others were able to come up with the second one. So I think it would be useful to take a look at both of them. I'm not gonna go in depth into the first solution. I'm just gonna give you the general idea, and hopefully you can build up from there. And we're actually gonna look more closely at the second solution. So let's take this tree for example. The idea of the first solution comes from defining the notion of position first. So I want to define what the position of an element is, and simply the position of the kth, the position of an element is its position in an in-order traversal. So it's a pretty intuitive definition. So if I perform an in-order traversal of this tree, it's gonna go 1, 5, 6, 7, 8, 9, 10, 11, 12, 15, 15, 16, 17. So the position of 8 is simply 5 because in the in-order traversal, it was at position 5. So this is the idea behind position. So when I'm asked to find the kth smallest element, I could simply find the element with a position equal to k, right? And this is basically the same thing, and it even takes care of repetitions. So you might be tempted to define position as like the element having a position equal to k is the element with k minus 1 elements less than it. But this would kind of break down because of repetitions. So defining it through an order traversal would help us avoid this issue. So anyways, the idea is if I can somehow evaluate the position of an element, so let's say somehow I find out that the position of the root is 8, which is true by the way. Then since the position of this node is 8, then I know that the kth smallest element, if k was 10 for example, I know the kth smallest element is to the right. Why? Because if this is the 8th smallest element, then all of those nodes have positions that are less than 8. So I know that I have to go right. So if I go right, let's say I evaluate the position of this node quickly. Let's say there's some O of 1 way to evaluate the position of a node. Then I would know that this node is at position 11, yeah. Then, and you can verify this through looking at the in-order traversal. So then, I know that I have to go left. Why? Because if I go right, I'm gonna go to positions that are greater than 11, and I already know that the position I'm on is too big. So I go left, then I evaluate this position in O of 1, and I can tell that this is the element I'm looking for, right? So this is the idea. But how do we find the position of an element in O of 1? So I don't wanna spoil this. I'm gonna want you to figure this out on your own. And if you have any questions, feel free to reach out. But the idea is you only need two things. You need the position of your parent. So I know that in this case, the position of my parent is 8. And you need to know if you're a left child or a right child. So I'm a right child, and the position of my parent is 8. And I have access to these sizes. So you also want to know that you have access to the sizes. So using these pieces of information, how can I figure out my position? And my claim is that you only need these pieces of information. You don't need anything else. So try to figure out how you would do this. For both cases, if you're a right child or a left child, if you can find an O of 1 way of finding your position, knowing only these pieces of information, then you've basically solved the problem. You just find the position of the node you're currently on, then decide if you want to go left or right, and then just do this over and over again. And this would be O of h, which is O of log n, because this is a balanced BST. So this would be a valid solution to the problem, but it's not the one we are gonna go deep into. So actually, no, let me keep this. Let me just erase those. So this other solution we're gonna talk about is based on changing the value of k. So the intuition is, if I'm at this node, I know that there are seven nodes that precede me in an in-order traversal. Then I know that I want to go right. If, for example, k is 10, I'm still on the same example. K is 10, the position of this element is 8, so I know I want to go right. But the thing is, when I go right, I can solve this problem recursively by simply changing the value of k. So, I wanted to find the 10th smallest element in the entire tree, right? Now, when I go right, if I zoom in on only this tree, if I consider only this tree, so my problem is now reduced to finding the kth smallest element in this tree, I would still need to change the value of k, because the 10th smallest element in this tree, even though there are no 10 elements, but in general, the kth smallest element in this subtree is not necessarily the same element as the kth smallest element in this subtree. So k is gonna have to change. So how exactly should k change? The idea is, if you're looking for the 10th smallest element, and you've already disregarded 8 elements, then you would have to look for the k minus 8th smallest element, which is the second smallest element in this subtree. Why? Because the second smallest element in this subtree, which is 15, is the 10th smallest element overall, because we already know it's greater than 8 other elements. Right? So the idea is, if you know you wanna go right, once you go right, you have to change the value of k by subtracting the position of the node you're going right from. Hopefully this makes sense. Another case you may be in is if you go left. If you go left, so if I want the 10th smallest element in this subtree, if I want the 10th smallest element in this entire tree, then when I go left, I'm gonna want to find the kth smallest element, but now I'm limited to this subtree. So though I have to change the value of k, I really don't, because there's no reason to change the value of k. The 10th smallest element here is, actually 10 is a bad example when going right, so let's say k is 3. So the third smallest element here is the third smallest element here. So yeah, I believe this basically completes the intuition behind the algorithm, and let's implement it so it's more concrete. So we're gonna define select of root and k. So first of all, let's figure out the position of root. So we're gonna check if, so let's say the position of the current node is the size of its left subtree. And here let's just assume size is defined to be 0 for none. So actually let's call it x. And x is defined like previously mentioned. So position is equal to x plus 1. If position is equal to k, then we return root. Otherwise, if position is greater than k, so for example here, I was at 8 and k is 3, so I want to go left. So I'm gonna return select of root dot left and k. Else, then position is greater than k, then I simply return select of root dot right and k minus position. So this is simply the idea behind the algorithm, and assuming k is valid, so k is less than the size of the tree, then we should terminate here at some point. But just in case, we can add this check that if k is greater than root dot size, we just return, let's say, null, just to indicate that something went wrong. Okay, so hopefully the intuition behind this algorithm makes sense. One thing to keep in mind is pause is not necessarily the position of the node with respect to the entire tree. So while we're going through our recursive calls, we might reach a point where pause is the position of the node, but not with respect to the entire tree, rather with respect to the subtree that we're currently dealing with. So, and this difference between the actual position in the entire tree versus the position in the subtree we're currently dealing with is being accounted for when we are changing k. So we're changing k in a way that this difference in the position with respect to the entire tree versus the position in the subtree we're working with in a specific recursive call, it's being accounted for by that change in k. So that's one way to look at the change in the value of k and what this POS variable really represents across recursive calls. A few other things to keep in mind regarding how you actually write your answer for this question. It might be a good idea to explicitly state that x is the same x we defined in part A, or as I said, you could go with the route of defining the size of null to be null, the size of null to be 0. Also, it might be a good idea to check if the root is null as like the first step in the function, and if it's null, we can just return null. So, part D. To maintain the correct sizes for each node, we have to modify the red-black tree operations, insert and remove. For this problem, we will consider only the modifications to RB insert, i.e. you are not responsible for RB remove. Recall that RB insert first uses regular insert for binary search trees, colors the new node red, and then fixes any violations if they occurred. How should we update insert to maintain correct sizes for nodes? During the fixing phase, RB insert performs recolorings and or rotations. For each case, recoloring or rotation, describe what updates, if any, need to be made to the sizes of the nodes. For rotations, it is sufficient to describe the updates for left rotations, as right rotations can be treated analogously. Okay. So let's go back to the tree we were looking at as an example. So this tree. Let's say we want to insert some node. Let's say the value of this node is 13 maybe. Yeah, let's say we want to insert 13. So first of all, we simply insert using regular BST insert. So we're gonna go this way, then this way, then this way, then this way, and we're gonna insert 13 here. So the first modification we're gonna have to do is while inserting, we're gonna have to update the sizes of these nodes. Because every node we pass through is gonna have its size increased by 1. So while passing through the nodes, just increase the sizes. This is gonna be 6, this is 3, this is 2, and when inserting this, insert it with a size of 1. So hopefully this is clear. Now after this, according to red-black tree algorithms, we're gonna color this red, and then we might have to do some recolorings or rotations. So for recolorings, do we have to change anything? If we recolor, then no nodes are gonna move around, no sizes are gonna have to be changed. So for recolorings, nothing has to be modified. First of all, the first thing we established is that while inserting using normal BST insert, we're gonna have to update the sizes. Second of all, if we recolor, nothing has to be changed. Now we're gonna have to deal with rotations. Let's say we have this tree. Let's say we have X, then it has a child Y and Z, and we're asked to deal with right rotations. So we're gonna rotate this way. So let's say we have these children A and B. Okay, and if we rotate to the right, oh sorry, to the left, then Wait, are we asked to deal with right or left rotations? Oh yeah, we're asked to deal with left rotations, so it's that way. Okay, so we're gonna have y, then x, then z, then b, and then a. So the question is, what sizes are gonna change and how are they gonna change? So first of all, the size of this subtree at z is not gonna change. So this is fine to keep as is. For a and b, it's the same thing. These are not gonna change. But for x and y, x has changed. The children of x have changed and the children of y have changed. So these two, their sizes are gonna have to change. So let's take a closer look at this. For x, it used to consist of the size stored in x was the size in z plus the size in y plus 1. Now, it's the size in a and z. Right? So the size in x is going to be updated to become the size in z plus the size in a plus 1. And the size in y is going to have to become the size in x, y dot size, equal to x dot size, sorry, y dot size is equal to x dot size plus b dot size. So again, those three, their sizes are not going to change. Those two, we're going to update them according to the relationship O plus 1, according to the relationship we established at the beginning of the problem. Yeah, and I believe this ends this problem. Actually, I do think, I'm not sure if we went over why, for part B, why our algorithm is O of n. The idea here is, our algorithm is similar to an in-order or a pre-order traversal. So we're going over every node once. We're only taking care of a node once, and we're doing an O of 1 operation at that node. That's why it's O of n. For our next problem, we're going to be solving problem 3 from the fall 2020 quiz 1. So this is problem 3. You are given p3.cpp file for this problem. So this is the file that we were given. Okay. In this problem, you are given an abstract class shape, which is used to represent 2D shapes. You are also provided with the class point. So this is the class shape, this is the class point. You are also provided with the class point, which represents a point on a plane. Shape has 3 purely virtual functions. Compute area, which should return the area of a shape. Inscribed circle, which should return the diameter of the largest circle that fits inside the shape. And print. So this class is abstract because it contains at least one purely virtual function. Actually, it contains 3. And these are the 3 functions that we're gonna have to implement. And note that any class that inherits from shape, it has to implement these functions, or otherwise this derived class is also gonna be abstract. So it's okay to not implement them, but the class is gonna be abstract. Okay, so for part A, we're gonna write a struct rect, which represents axes aligned rectangles that which are rectangles whose sides are parallel to the x-axis and y-axis. To represent such a rectangle, rect has 3 member variables: 1 point to represent the bottom left point of the rectangle, and 2 numbers to represent the length of its sides. Implement all the necessary functions. Okay, so we're gonna have this struct rect, which inherits from shape. They didn't really specify if the member variables are private, but yeah, we might as well make them private. So we're gonna have a point which represents the bottom left. We're gonna have a double for the width and a double for the length. And instead of naming those width and length, you can name them, like for example, length 1, length 2, or dimension 1, dimension 2, because width is usually smaller than the length. So depending on if you're gonna make sure, so it depends. If you want to make sure, if you're willing to make sure that width is smaller than the length, then you could name them like this. Otherwise, it might be better to name them L1, L2, something like that. But yeah, the naming doesn't really affect the functionality. It's just about writing clear code. So we have those private member variables. Let's implement those purely virtual functions. So first of all, we have double compute area. And note that here the function is double compute area const. So it's specified that this function is not gonna alter the state of the object. So we have to include this const keyword here as well. Otherwise, this will not be considered as providing an implementation for this function, because this const keyword, it matters. So we're gonna have to put this here. We're gonna just have to return the width times length. We also have to implement inscribed circle. Okay, so the diameter of the largest, oh sorry, where were we? Yeah, print should print the coordinates of the bottom left point and the length and the width of the rectangle. We'll come back to this. The diameter of the largest circle that can fit inside the rectangle is equal to the length of its shortest side. So here we just have to return width, assuming that we are gonna take care of the fact that width has to be less than length, or equal to it. Okay. Now back to print. I believe there's an example here for how we're supposed to print the rectangle. So let's stick to that. Oh, also I forgot the const keyword here. So it's easy to forget, but try not to. And if you forget it, the compiler is gonna complain that rect is an abstract class, and this would be an indicator for you that there are some purely virtual functions that you didn't provide an implementation for. And this should be one of the things you look for. Make sure that you didn't forget those. Okay, so void print. So we have to see out bottom left point, and then we're gonna print this. Then we have width. Let's continue this on the next line. We have width is equal to, and then the width, and then length is equal to, and then the length, and then a new line. Okay. What's the issue? Oh, so there is no we didn't overload the insertion operator for a point, and that's not provided. So let's do this now. So as you may recall, it returns an OStream reference. Operator insertion. It takes an OStream reference OSTR. It takes a const point reference, let's call it P. And so this is the structure. Now here you wanna put p.x, and here it's gonna be p.y. And note that those member variables are private, so we're gonna have to friend this, and we're gonna need a semicolon here when we're friending. And what's the issue here? Expression must have integral unscoped enum type. Oh, sorry, this should be a reference, not a pointer, my bad. Okay, now, and then we should change it here as well. Now everything should be fine. Okay. So we've implemented inscribed circle, implemented compute area, we've implemented print. Hopefully this is all functional. Okay. Write a struct circ which represents a circle, hence it has two member variables, one point representing its center and one number representing its radius. So let's implement this here. Struct circ, and it inherits from shape. So it has two member variables. Let's make them private as well. We have a point center and we have a double radius. And we have to implement all necessary functions. So we're going to have to implement the purely virtual methods. So we have compute area, inscribed circle, and print. Okay, let's make them public. For compute area, we're going to have double compute area const. And they told us we can use 3.14 instead of pi. So we're going to return 3.14 times radius times radius. 3.14. Okay. For inscribed circle, what's the largest circle? What's the largest diameter of a circle that can fit in this circle? It's simply the circle with its diameter. We're gonna return 2 times radius. And then for print, let's check what the format is. So it's cout center, and then the point center, and then radius, okay, and then let's add an end line. Okay. Add a member function fit inside to circle which does the following. Given a shape, it returns true if the circle fits inside the shape, else it returns false. Okay. So we're gonna have this member function. It's gonna return a boolean. It's inside of, it takes a shape, but we are not really gonna change this shape, so we might as well make it const. We're gonna take a const shape reference, call it S. Also note that since shape is an abstract type, we can't really do something like this. So this, it wouldn't really be okay because shape is an abstract type, and an abstract type can't be instantiated. So it's either gonna have to be a reference or a pointer to a shape, and we can go with reference for here for now. So we have to check if this circle can fit inside the shape. So first of all, let's invoke inscribed circle. So we get the radius of the largest circle that can fit inside this shape, and we just have the diameter of the largest circle that can fit inside this shape, and we just have to check if our diameter, which is radius times 2, is less than or equal to this maximum diameter, and we just return this Boolean expression. So this is it. And let's add a semicolon. For part D, given an array of shapes, we would like to sort it according to the area of each shape. Since shape is abstract, we have instead an array of pointers to shapes as shown in p3.cpp. So let's see here. We have an array of pointers to shapes. You are provided with the code for templated insertion sort. So this is the code for templated insertion sort. Make the necessary modifications to your code, including insertion sort, so that calling insertion sort on an array of pointers to shapes will sort the array by area. Your modified insertion sort should execute correctly on an array of pointers to integers as shown in p3.cpp. So here we have this array of pointers to integers, and insertion sort should still be functional on it. So we want to generalize insertion sort in a sense. So the first modification we're going to have to do is this t pointer a, it's kind of like an array of objects. But we want it to be an array of pointers to objects. So we can make it t double pointer a. Also, this key is now going to be a t pointer key. Otherwise, we're just iterating. Key is equal to a at j. This isn't a problem because a at j is of type t pointer and key is also of type t pointer. Everything seems to be fine here. And then here, we don't want to compare a at I and a at key. We want to dereference a at I and dereference a at key and compare the objects there. And the rest is just insertion sort logic. So what we're doing here is, if t was an integer, then we're comparing integers. Otherwise, for example, if it's a shape, we have to define what it means for a shape to be greater than another shape. So we're going to have to overload this operator. And it makes sense to overload it on shapes and not on rectangles or circles, because we might have a lot of different shapes or a lot of different structs or classes that represent shapes. So we want this overload operator to be generalized on all of them. So we're going to have bool operator less than. Was it less than or greater than? Oh, it's greater than. So bool operator greater than. Let's overload it within the shape class, because here this operator is going to be invoked through the left hand side, as we previously discussed regarding the insertion operator. So bool operator greater than, it takes a shape, a const shape reference, let's call it other, and it returns other.compute area. Actually, let's say compute area is greater than other.compute area. Well, let's call this, okay. And this is going to be a const as well, because we're not really changing the state of the object. So we're just going to check if compute area is greater than other.compute area. That's how we're defining a shape to be greater than another shape. So this should be fine now. And I noticed that in main we have some red squiggly lines. This is because main is invoking constructors for rect and circ that we haven't implemented. So now that we've noticed this, let's just implement them. We're gonna have, actually let's put them at the top. We're gonna have a rectangle. It's gonna take a point P, a double, let's call it L1, and a double L2. And then bottom left is equal to P. Width is equal to the minimum between L1 and L2. And length is equal to the maximum between L1 and L2. Okay. And let's do the same for circ. It's gonna take a point P and a double R. And here let's use an initializer list, center P. Could have used an initializer list. Could we have used this here? I think calling a function in an initializer list is not really allowed, so it's better to do it in the body of the constructor. So yeah, so center P, radius R, and that's it. So let's go back to the problem. Write a code that prompts. Oh, actually, let's run this first. Make sure everything is functional. Okay, so there seem to be some errors. operator. Oh, so I forgot to return OSTR here. Oh, I forgot to remove P1. Let's just remove it. Now hopefully it's gonna run. Okay, so let's compare it to the expected output. So compute area of R should give us 8. Good. Inscribed circle should give us so we have this point. Oh yeah, the largest circle that can fit in R has a diameter of 2, which is good. Can C1 fit inside R? C1 has a radius of 1, so yeah, it can fit. Can C2 fit inside R? It has a radius of 2, meaning a diameter of 4, so it can't fit inside R, which is false. So yeah, and then we print them in sorted order. So it's should print C1 first, then R, C2, C3. Yeah, so C1, then R, then C2, then C3. And for the integers, they're printed in sorted order as well. So everything seems to be fine. Now for part E, write a code that prompts the user to create shapes and stores them appropriately. First, it asks the user for the number of shapes they wish to create, say n. Then for n iterations, it asks the user which shape they would like to create, circle or rectangle. If they enter circle, they are prompted to enter coordinates of circle and radius. Similarly, if they enter rectangle, they are prompted to enter the coordinates of the bottom left point and the width and height and length. For partial credit and a good starting point, first solve this for some fixed value of n, say n equal to 2. This is the provided sample output where R is used to denote rectangle and C is used to denote circle. So the user is asked how many shapes they would like to create, and then they provide the needed info for the shapes. For the circle, the user is asked to enter a radius and the center coordinates. For the rectangle, user is asked to enter the coordinates of the bottom left point and then the dimensions of the triangle. And then the user input is printed in sorted order, but the problem statement tells us we're not asked to print the user input in sorted order, but simply to store appropriately all the inputs from the user. Okay, so first of all, one thing that's important to note is we can't create an array of shapes or a vector of shapes, because shape is an abstract class. And we can't create arrays or vectors of abstract classes. So the way we're gonna have to approach this is we can store the objects in a vector of shape pointers. So one way to do this is let's create a vector of shape pointers, and then when the user asks us to create a shape, we're gonna create it and add it to this vector. Let's start by including vector. And okay, let's implement this here. So first of all, we have this vector of shape pointers and not shapes, because we can't have a vector of an abstract type. So vector shape pointer, let's call it v. And then we're gonna have an integer n. We're gonna ask the user how many shapes do you wish to create. After that, we're gonna read in the integer that the user entered. Then we'll have this for loop run for n times. Oh, actually, we need an n here. Okay. So then we're gonna ask the user which shape do you want. We're gonna read in the response in a character variable, and we're gonna check if response is equal to C, then the user wants to create a circle. Else if the response is equal to R, then the user wants to create a rectangle. Otherwise, we're gonna tell the user that their input is invalid, and we're gonna give them the chance to provide input again for that shape. So we're gonna say I minus minus, so this loop basically doesn't count towards the total number of shapes. Okay, so after that, let's take care of every shape. So if the user asks us to create a circle for them, then we're gonna ask about the radius. And let's create a double R. Let's actually call it radius. Then we're gonna read in the radius. Then we're gonna ask about the center coordinates. And let's create variables for the coordinates of the center. So double xy, cnxy. And then we're gonna create this point object. We have a point center xy. And then let's create the circle object. So we're gonna give it the center and the radius. And note that so far what I'm doing may seem correct, but it's not completely correct. And we're gonna see at the end what could go wrong. So anyways, if the user asks us to create a rectangle, we're gonna ask about the coordinates of the bottom left point. And then we're gonna ask, we're gonna read in those coordinates, cn xy, cn x y. And then we're gonna ask about the lengths of the sides. We're gonna have doubles L1, L2 for the lengths, and then we're gonna read them in. Okay. After that, we're gonna create the point for the bottom left point. So P, X, Y, and we're gonna create the rectangle. Okay. So now we still have to add the circle and the rectangle to the vector. So let's just do V dot pushback circle. We're gonna have to push back the address of circle, because remember this is a vector of shape pointers. And we're gonna do V dot pushback the address of rectangle. Okay, and at the end, let's just print them out to make sure that we're storing them correctly. We're not gonna sort them. The problem doesn't ask us to sort them, so we just want to make sure that everything is running fine. So let's see out not v at I. We have to do v at I dot print. But it's not really v at I. It's we have to dereference v at I and then print it, because remember v at I is a pointer to the shape object, so we have to dereference it and then call print. So let's run this, make sure it's all fine. Okay, so it's asking us how many shapes we want to create. Let's say 3. which shape do you want? Let's say we want to create a circle. Let's say the radius is 3, the center is at 0, 1. Now let's create a rectangle. The bottom left corner is at -10, -9. The sides, let's say they're 4 and 5. Which shape do you want? Let's say we want a circle again. The radius is 100. The coordinates are at 0, 0. So notice that this is supposed to print the first circle, then the rectangle, then the second circle. But what actually happens is instead of the first circle, it seems like it's being overwritten and we are printing the third circle instead of it. So what's actually happening here? The issue with this is here, circle is a local variable. So it's kind of like we're using the same memory. It's kind of like we're using the same place in memory with every iteration of the for loop. So when we instantiate the circ object and we push back the address, then with the next iteration, when we create a new circle, we're gonna be creating the new circle in the same place in memory. So this memory address is gonna be the same for both circles, and only the latest changes are gonna be updated. And we can actually see this, I believe, if we print out the memory addresses themselves. So if we try to do this, see where each shape is stored in memory. Okay, so how many shapes do you wish to create? Let's say we want to create 3 again. Let's say a circle, radius is 1, coordinates are at 1, 1. What shape do you wish to create? A rectangle from 0, 0, 5, 4. Another circle at center at, radius is 9, center at 8, 8. So you can see that the address of both circles is the same. The address of the rectangle is different because it's a different variable. But because we're using the same variable for both circles, then the address is the same here. So how can we solve this? We can dynamically allocate the memory for each of the shapes. So here, instead of having circle be created this way, we can do circ pointer circle is equal to new circ, and we pass in those. We pass in center and radius, and then we push back circle because circle here is itself a pointer. The same thing for rectangle. We can make it rect pointer rectangle equal to new rect, and we pass in those variables, and we push back rectangle. And now since we're dynamically allocating those shapes, we're gonna have to take care of deleting them. So we're gonna have to loop over them. Once everything is finished, we have to loop over them. So for int I equal to 0, I less than n, I plus plus, we have to deallocate that memory. So delete v at I. Okay, now let's try to do this again. So v at I. Okay, this is not doing what I want it to do. Okay, so dereference v at I dot print. Now let's try to run this. So what shapes do you wish to create? How many shapes actually do you wish to create? Which shape do you want? A circle, radius is 1, center at 0, 0. Let's say a rectangle at 7, 8, 9, 10. Which shape do you want? Let's say a circle, radius is 90, center coordinates at 9, 8. And now it works properly. So the first circle is printed properly, then the second rectangle, then the third circle. And I believe this problem is done with that. Okay, yeah. So that's all for today. Hopefully you found those problems beneficial. If you have any questions, feel free to reach out, ask me anything you want, and hopefully everything is a little bit clearer now. I wish you luck in your exams.